Alright, in this video we'll be looking at the surface area of a sphere. Now we're not going to start with a full sphere, we're only going to focus on half a sphere, a hemisphere for now. We'll say the radius is r, and what we're going to do is construct a cylinder with the same radius, and we're going to make it so that this cylinder is also just as tall as the hemisphere, so that means its height is also r. Now clearly the cylinder has a bigger volume, but we're going to put this drill right through it. The drill is made with the same radius and height as the cylinder, it's a cone with the same dimensions, and one important thing is that it must be sloped at a 45-degree angle. That's going to be really important later. So we're going to run this drill right through the cylinder, and we're going to drill a chunk right out of it. And if you've been following the other videos, you probably know where this is going now. Okay, we're going to show that the volume of the cylinder, with the cone drilled out of it, is the same as the volume of the hemisphere. And we're going to do this by taking cross-section slices and showing that these slices have equal area. So let's say our slices have a height of x. Now it's important to keep this x as a variable because as x changes, the size of the slices also change. You can see for both shapes that if you move the slice up the object, the area will decrease. Alright, so look just at the cylinder slice for now. Now because the cone is at a 45-degree angle, the radius of the hole, the inner radius, will just be x as well. Now of course the large radius is just the radius of the entire cylinder, which is going to be r. This means the area of that donut slice is the big circle minus the small circle, which is pi r squared minus pi x squared. We can factorize out the pi, and so we make brackets, and inside those brackets it's r squared minus x squared. Okay, that's going to be important later as well. Alright, we'll stop there, move across to the sphere. The distance from the middle of the sphere to the edge of the circle, right? Now if you look carefully, the edge of the circle is on the edge of the sphere as well. So the distance from the middle of the sphere to the edge of the circle is just the radius of the sphere, which is r. But what we'll be needing to use is not this radius, it's this smaller radius on the circular slice drawn in orange. And the area of the circle is now pi times this orange radius squared. But if you look carefully, you'll see that this orange one is just part of a right-angled triangle, so in fact the orange radius is linked to the other measurements with Pythagoras, and now r is the hypotenuse, so our radius square is just r squared minus the x squared. Okay, but that's exactly what we got on the cylinder side, which means that the two slices have the same area. Now this works for any value of x, so if we grab all those cross-sectional slices on the cylinder, with the cone drilled in, remember, they can all equally transform into the cross-section slices for the sphere, demonstrating then that their volumes are the same. So what is this volume of the cylinder with a cone drilled out of it? Well, the whole cylinder is pi r squared times r, and the cone is just a third of that. So the volume will be the cylinder minus the cone, and now r squared times r is just r cubed. Then if you take away a third of pi from a whole pi, you're left with 2/3 of pi. And this is identical now to the volume of the hemisphere, which means the volume of the whole sphere must be double that. So we have 4 pi r cubed over 3. So that's the volume of a sphere. Thanks for watching, and I'll see you later.